How's it going, ladies and gentlemen? Mr. Donnie here with some Chapter 11 problems. We're going to be looking at intermolecular attractive forces and liquid and solid specifically. So let's start with number one. It says, as a solid melts, the atoms become blank and they have blank attraction for one another. Well, if we were to magic school bus it down to the size of molecules and stuff and look at how they look in a solid structure, they're packed real tight, nice and neat and orderly. And when they become a liquid, they start to move around and become a little disorganized, right? Because they're no longer attracted to each other as much. They're free to move around. Over here, as a solid, real rigid structure, they're really attracted to each other strongly, and they're not going to move past each other, but in the liquid they will. So which one does this correspond to? B. They become more separated, and they have less attraction for one another. All right, 2, it says, as a gaseous element condenses, the atoms become blank and they have blank attraction for one another. It's kind of the opposite of the last question. So if we were to look over here, this is kind of what it looks like to be in a gas phase. They're spread out, they're moving around randomly, straight line motion till they hit something. And then as a liquid, they're at the bottom of the container and they're flowing past each other. They're a lot closer together because they have more attraction for each other. So the atoms become closer together and have more attraction for one another. I did some TV movie magic and already wrote out these structures so we can look at the question. Which one of the following exhibits dipole-dipole interaction between molecules? So the first question is, well, when do we have dipole-dipole interaction? It's when you have a polar molecule. So in order to be a polar molecule, you need to have polar bonds and at the most, one line of symmetry, So we're looking at these options. Well, which one does that apply to? Well, if I had XeF4, I got multiple lines of symmetry here. This is a square planar molecule, so it's going to be nonpolar. If I look at ASH3, there's only one line of symmetry there, polar bonds. So this would be trigonal, pyramidal shape, and it would be polar because it only has that one line of symmetry. CO2 is linear. It's got multiple lines of symmetry, so that's definitely nonpolar. BCl3 is trigonal, planar. So it has at least 3 lines of symmetry, which means it's nonpolar. And Cl2 is linear, and there's a bunch of lines of symmetry there, so it's nonpolar. So which one of these things is polar and give you dipole-dipole interactions? ASH3. Of the following substance, only blank has London dispersion forces as its only intermolecular force, So London dispersion occurs in all molecules, including nonpolar molecules. And when it's the only intermolecular force, then it has to be nonpolar. So again, we're looking, our cheat is lines of symmetry with our Lewis structures. If we have more than one line of symmetry, then it's nonpolar. So we look, well, CH3OH has no lines of symmetry, so this is definitely a polar molecule, so it can't be it. NH3 has one line of symmetry. It's a polar molecule, so it'll have hydrogen bonding and dipole-dipole. It's not going to have only London dispersion. SH2, that's going to be a polar molecule. CH4 has multiple lines of symmetry, so it's nonpolar, and that would be our answer. It's the only one that has only London dispersion. So if you take a look at HCl, it has a polar structure. It's linear with one line of symmetry, so it's polar, so it wouldn't be that. All right, which of the following should have the lowest boiling point? So we want the lowest boiling point, which means we have the weakest attractive forces, intermolecular attractive forces. So remember, in order of strength, we kind of have the electrostatic, which would be for ionic compounds. Below that, we would have hydrogen bonding, when you would have a polar molecule with hydrogen bonded to a nitrogen, oxygen, or fluorine. What else? Dipole-dipole would be the next step down, and that's when you have a polar molecule. And then we have London dispersion, which is for nonpolar molecules. So strongest is up top, weakest is down here. So we're looking for which one of these things has only London dispersion forces. So if we have pH 3, that's going to be polar. And well, let's see. So we know it's either going to be dipole-dipole or hydrogen bonding. It's not a hydrogen bonding, so we're going to have dipole-dipole. SH2 polar molecule, not hydrogen bonding. So again, that's dipole-dipole. HCl has, so again, a polar molecule. It's not hydrogen bonding, so it's dipole-dipole interaction. SH4 has many lines of symmetry, so it's non-polar, which means it only has London dispersion. And then if we take a look at H2O, it's polar, and it is that special case where it has hydrogen bonded to either a nitrogen, oxygen, or a fluorine, so it's got hydrogen bonding as its strongest attractive force. So which one of these things is the lowest boiling point? Well, the one with the weakest attractive force, which would be SiH4. 6 of the following substance blank has the highest boiling point. All right, so again, highest boiling point would be strongest attractive force. So if we see any ionic compounds on there, which we don't, all right, next step would be hydrogen bonding. You know, do we have any hydrogen bonded to a nitrogen, oxygen, or fluorine? We sure do. Look at it right here, H2O. So if we had to predict, H2O out of these would have the highest boiling point. Yep. Because, all right, well, I just caught something. Well, Mr. Downey, what about NH3? Doesn't that also have hydrogen bonding? Yeah, it does, right? Because we got hydrogen bonded to a nitrogen, oxygen, or fluorine. Now, generally, we also want to take a look at the size of these things. So the size or mass, I should just say mass, as the mass goes up, the attractive forces go up because you have more electrons to polarize the molecule. So the more electrons you got, the more polarizable you are, which means that you can have stronger London dispersion forces. So if we take a look at the mass of NH3, that's like 17. Then for water, it's 18. So A would be the strongest. 7 of the following blank has the highest boiling point. So again, it's another one of strongest attractive force. So, well, let's see. N2, Br2, H2, Cl2. I see a pattern here. These are all nonpolar things, so they're all going to have London dispersion forces. And we know that as the mass goes up, the London dispersion force goes up too. So we're looking for the most massive of these things. All right, well, that's just a matter of looking at the masses and getting the GFM. Br2 is the greatest. Now, the reason for that is, like, picture you got just hydrogen, right, with one electron going around it. All right, well, at any given moment, the electron might be like on this side, and then that would make it slightly negative and that end slightly positive. But let's just use an example like helium. If we had 2, all right, well, at any given moment, those 2 might be on one end together, you know, which would make that end much more slightly negative and the other end slightly positive. So the more electrons, the bigger the mass is we got, the more polarizable it is, which means we can get these bigger charge differences momentarily, which is going to hold those molecules together more strongly. 8, which of the following derivatives of ethane has the highest boiling point? Again, so we want strongest attractive force. All right, they all seem to be nonpolar molecules. Right, it's just 2 carbons with 6 bromines or 6 fluorines, 6 iodine, 6 fluorine or 6 hydrogen. So again, highest boiling point would be strongest, which, all right, well, if they're all nonpolar, they're all London dispersion. So we want the most massive one to give us the strongest attractive force. Which one of those is it? C. And 9, when NaCl dissolves in water, aqueous Na plus and Cl minus ions result. The force of attraction that exists between Na plus and H2O is called blank interaction. All right, so if we take a look, the ionic solid for NaCl will kind of look like this, right? And then electrons. Now, what's holding these things together, the sodium and the chlorine, is the electrostatic force. You have these permanent charges on the ions that are attracted to each other, holding each other together, right? They're being pulled together because of that charge difference. Now, when water comes around, what happens is, well, water is a polar molecule. So one end of it, the hydrogens are going to be slightly positive, and that oxygen is going to be slightly negative. This is going to interact with the charges that are already there. The negative chlorine is going to interact with the positive hydrogens, and the negative oxygen is going to interact with the positive sodiums. So you're going to get something that can kind of look like this. You're going to have one water molecule that's surrounding a chlorine ion and keeping it separate from the sodium ion. So that's holding it together. And now the other end of a water molecule, the negative end, would be attracted to the Na plus interacting. All right, well, how would we describe these interactions? Well, let's see, we got an ion and we have a dipole. So what could we call it? I don't know. How about ion dipole interaction? Crazy, real creative, I know. Probably lost you there with the naming part of the force. All right. All right, well, I hope you found that helpful, and I will see you in class. Bring questions.